we have, so first thing will be to remind or talk about Hilbert Serious theorem. So the situation will be like this. We'll work over the ring Kx1xn. So that's just a polynomial ring and n variables over a field K, and actually we might take K to be just the complex numbers. Okay, so this is a graded ring. We treat it as a graded ring, so it will be direct sum of AI, where AI is the homogeneous polynomials of degree I. And well, we'll be concerned with the modules, graded modules over this ring. So what I mean by that is we take M to be also direct sum of Mi, but maybe I starts at some D0, and some integer. It might be 0, might be some other number. And of course, it's a module, so we have to have multiplication AI times Mj, and it will have to go to Mi plus j. I and j are integers here. So really, each Mi is a finite dimensional vector space over K, and the multiplication acts like this. So this is a graded module. And already Hilbert, in this situation, in his great paper in, I think, 1890, he, well, considered how far is such a module from a free module. A free module would be direct sum of copies of A, but there's one caveat here. Since I'm talking about graded modules, I will always say that A minus D will be just A, but with a generator in degree D. So 1 will be basically in degree D. Because whenever I talk about maps of graded modules, I will want this map to take a component of degree I to the component of degree I. So then how do we measure how far is this? So a free module would be something like A minus D1 plus A minus ds. That's a free module. It has a basis, so there's nothing interesting really about it. If you know this ring, you know this module. But okay, so how do we deal with a module which is not necessarily free? What happens? I mean, so Hilbert noticed already this thing that, so what we can do when we have a module M, we can first of all cover it by a free module. But we do it in a graded way. So we basically, well, you start in the lowest degree, you take a basis of this space MD0, so you take this many copies of the module A minus D0, then you see what you covered in the next degree and so on. And you can always do it in the kind of smallest way. So there is something that is a minimal cover. So, and this F0, let's say it has to be a direct sum of those modules, but let's look at let's give some names. So suppose I call those numbers B0. I call this module F0. So kind of degree by degree, I choose the generators in the most economical way. I assume actually that this module M is finitely generated, so this will be finite module. I can always do that. And then I have the kernel M1, which will be some other graded A module. So then I can do now the same with M1. And I can, this M1, I can cover with the free module F1, also in a minimal way. So this will be A minus J to beta 1J. And then I have the kernel M2. And I continue. And the point is now that this process stops. So Hilbert Serious theorem tells you that if you are over a polynomial ring in n variables, then necessarily the module Mn, after n steps exactly, you will get a free module. You could get 0 already before. So Hilbert Serious theorem. Mn is free. Free graded module. it could be 0 already earlier, but so in fact, when you put all of this together, you can deduce that the module M has what's called a minimal free resolution, namely, it will be an exact sequence of those graded modules. Here I have my F0, and now you see I have here the map from F1. I can go to M1, and I can compose, embed M1 in F0, so I get a map from F1 to F0. I call it D1. And since after n steps I get the free module, I can end with this, call this Mn Fn. And, and again, I remind that this will be A minus j to some beta 0j. This will be sum of A minus j to the beta 1j, etc. And this will be direct sum of A minus j, and I call those numbers beta nj. Well, it's all quite abstract, so let's give you some, let's look at some examples, very simple examples. Let's take, for example, the easiest situation. Let's take, so examples. Let's take first example, n equals 3, and let's take, so A is kx1, x2, x3. The point is that, and let's take M to be just k. So this means all variables act as 0. So what will happen here? So I have my module M, maybe. And you see, obviously, it's a one-dimensional vector space, so it has one generator. And say in degree 0, assume that it's degree 0. So then I cover it with A in degree 0. But now, of course, this is just a vector space. This is a polynomial ring, so there is a kernel. And the kernel will be anything that is generated by the variables. So what I can do, I can cover the kernel by A cubed minus 1, and I write always maps of free modules. You can always choose a basis, and you can treat it as a matrix of polynomials. And in fact, here the polynomials will be always homogeneous. And you see that's why I choose this notation. This is in degree 1, so this goes to an element of degree 1, say x1. So now you see I want to see how it continues. So I need to look at for the relations between those. So any element of the kernel here will be some linear combination of x1, x2, x3 with polynomial entries such that it will be 0. So, but these are variables. So, well, one can guess, I mean, it's not a proof, but one can guess that the only relations are trivial. So combinations of trivial relations, because I can always have the relation x2 times x1 minus x1 times x2 is 0, right? That's a stupid relation, so, but it turns out these are, so there are 3 of those. I write them in the matrix form, so I get x2 minus x1, 0, x3, 0 minus x1, and 0, x3 minus x2. Right? So this means that x2 times x1 plus x1 minus x1 times x2 is 0 when you compose those matrices. And it turns out that the thing ends very nicely here. And it will be x3 minus x2, x1. And so this is called a Koszul complex on the variables. And you see, of course, it generalizes to n variables. You see binomial coefficients here. But this is a very nice, already also, this was already known to Hilbert. So that's one example. You know, you can get slightly more complicated. Let me just write 2 more examples. And then let's just take some example for n equals to 2 even. Let's take again M to be A divided by x1 squared, x1, x2, x2 squared. Here, remember, A is, of course, kx1, x2. So this resolution will be even shorter. So I have A, so I have M. So again, it's a cyclic module, so I just cover this one generator. I just cover it. And of course, the first step, now you see all generators are quadratic. So I get a cubed minus 2. And here's my matrix. And now, well, it turns out that one doesn't have to look too much. All the relations in such a simple case are linear. You see what I can do? I can multiply this by x2 and subtract this multiplied by x1. That's one relation. Or I can multiply this by x2 and multiply this by x1 and subtract. And well, okay, it's not obvious, but one can prove that in this case, this will be the resolution. Okay? So, so this is a finite tree resolution of a module. And then you see, what is the resolution of a module good for? Well, it allows you to calculate all numerical data about the module. Okay? For example, the most important numerical invariant of a module is the Hilbert series. So Hilbert series you see I have hm of t. So I have my graded module m. Basically what I do the power series. I take dimension over k mi times t to the I. And it turns out that this is always a rational function because actually one can see it from this resolution, because you see the point is like this. First I look at the Hilbert series of my ring. It's a polynomial ring, but you see this is very easy to calculate because, well, let me just write the formula and then I tell you why it's true. Basically it's counting the monomials. You see in degree d we have all monomials and n variables of degree d. So you see if you take a equals kx1, you will get the series 1 plus t squared plus t cubed, etc. So this is 1 over 1 minus t, right? We have a equals kx1 x2. You take 1 plus, now there are 2 monomials of degree 1. Now there are 3 monomials of degree 2, etc. So n plus 1 t to the n. And this is plus, etc. So this is 1 over 1 minus t squared. So then you generalize it and you get this. So now you see, when I have my free resolution, so notice then that you see, let me write that, h a minus d, then will be just t to the d times 1 minus t to the n. I just shifted the degree from 0 to d, so I just do that. So then you see, when I have my finite tree resolution, then if I look, remember the component of degree I has to go to the component of degree I. That was the agreement. So if I look at the component of the degree I get the exact sequence of the vector spaces over K, finite dimensional vector spaces. So if it's an exact sequence, I have to have plus minus the dimension. All their characteristic has to be 0. So what I'll have is that HMT equals summation I bigger or equals than 0 minus 1 to the I H FIT. Right? But now this is very easy to calculate because remember Fi was summation A minus J beta ij. So Hilbert series of Fi is 1 minus t to the n, and here I get summation beta ij t to the j. I just take the direct sum of this. So what I get is that I get 1 minus t to the n, and here I get summation over I minus 1 to the I beta ij t to the j. So the point is, if you know all those numbers beta ij, how many generators we got at every stage in the resolution in every degree, you basically know everything about the module. I should also point out, it's right away that somehow from the resolution you can very easily get this. But if you know somehow this Hilbert function of the module, it's not easy to get the resolution, because you see what might happen. It might happen that, say, some a minus d occurs in 2 neighboring modules in your resolution, and then you'll get t to the d minus t to the d. They will disappear. So you kind of, there are cancellations going on. And this somehow is an obstacle that one should be careful with. I mean, it's not easy to find, you know, say, the Betti table from the Hilbert function. But, okay, I mean, history of commutative algebra did not start with, did not stop with Hilbert. So there was a lot of results and a lot of research, and in the 1980s, of course, what happened is that the computers came to the stage. So actually in commutative algebra, somehow computer algebra systems are very strong. Macaulay 2 singular, so actually commutative algebraists, half of the time they spent with calculating with Macaulay 2. And if you input a module into Macaulay 2, the most compact way to get the data about the module is to get the Betti table. So Betti table of a module. This is basically those numbers beta ij organized in a table, which in principle should be infinite, but in fact is finite. So this is what I'll call beta of m. And you know, I assume now that m is summation mi, I bigger or equals than 0. Let's assume I can always shift the grading. So it starts this lowest non-zero components at 0. So you see this Betti table, that's how this will be beta 0, 0, beta 0, 1, beta 0, 2. All those numbers organized in such a way. So this basically what it tells you is how many generators in degree 0 my module has, how many generators in degree 1, generators in degree 2, etc. And then this Betti table is organized in such a way that here I get beta 1, 1. See, my resolution is minimal, you see. So the point is that somehow all the coefficients in those matrices, if you choose basis for your free modules, have to be homogeneous polynomials of positive degree. So that's why. So here basically beta 1, 1 will tell you how many linear relations, linear in the variables x1, xn, I'll have between those generators. And here I write beta 1, 2, beta 1, 3, etc. Beta 1 n plus 1, and I continue. So for my examples, if I had the Koszul complex, what would be the Betti table? It was very, very simple. So you see for the Koszul complex, so in example 1, Betti table is very simple. All maps are linear, so I just see 1, 3, 3, 1, and 0, 0, 0, 0 everywhere else, right? But in example 2, I had one generator in degree 0, but then the relations were quadratic. So there are 3 quadratic relations, so I write them here, okay? And then between those 3 quadratic relations, there were 2 linear relations. So this will be the Betti table like that, okay? So you can always do it. Let me write one more Betti table that I'll use later, because it will be something very similar to the second example, but with shifted grading, just to show you that maybe interesting thing can happen. So example, let's take, again, n equals to 2, so a equals k x1, x2. But let's take m equals a divided by x1 squared, x1, x2. But now I take x2 to the 4th. So then you see, that's right, it can happen for a module. Now you see I'll have slightly more complicated, I'll have 2 generators in degree 2 now among relations, and 1 in degree 4, minus 4. So this is x1 squared, x1, x2, x2 to the 4th. And here, well, again, the relations, the first one is x2 minus x1, 0. So it will be a minus 3, maybe a minus 3 here, plus, but now here I can multiply this by this by x1, and this by x2 cubed. So 0, x2 cubed minus x1. So this will be minus 5, because I took the generator in degree 4 and the coefficient was linear, so it's minus 5. So the Betti table for that would be Betti table will be like this. I have one generator, 1, 0, 0. But now here I have two quadratic generator relations and one of degree 4. And then here I have Betti table like that. Okay? So you see, even though resolution is very, very similar, of course, since I switch the degrees, I get different Betti tables. Okay, so so, you know, and so years went by and people actually calculated many examples and many very interesting examples in geometric situations, for example. If you look at the syzygies of curves, this is like the whole area in commutative algebra, right? And it's not easy to decide, for example, for a curve, what the Betti table is, right? There's like the whole, if you take, you know, for example, if you take a non-singular curve of genus G, X is non-singular curve of genus G, and then, you know, this curve has this kind of distinguished embedding into PG minus 1 by the so-called canonical divisor. So this means that I take the coordinate ring of this curve when you embed it will be exactly the image of x0, xg minus 1. And then you see these are very interesting examples. And one knows, for example, the Betti tables are not very complicated for such a thing. Riemann-Roch theorem tells you everything about the Hilbert series. So you always know the Hilbert series of this thing. And one knows that the Betti tables look like this. You have one, and then you see a bunch of, the relations usually are quadratic, and there's a bunch of kind of linear things going like this. And then you see you have one here, and it goes like, maybe like this. Yeah. So you know that you have just one strand, and the rest are zeros, and then actually there's also duality. But for curves, you don't know, and that's mainly, you see, the problem here. Basically, these are exactly those two modules in the same degree. One in the next syzygy and the other. So if you calculate the Hilbert series, this will cancel out. So you don't know how long the linear strand goes, right? So this is the whole area of very exciting research. I mean, so like what, 5 years ago, I think Clerc was improved that for the general non-singular curve of genus G, I think there are as many cancellations as possible. Those will disappear. And then there are very nice conjectures of Green and Lazarsfeld telling exactly in terms of geometry of the curve, you know, how far, for example, this linear strand goes. So the syzygies in such geometric situations have very, very nice, concrete, also geometric meaning. But these are, you know, kind of difficult problems, even for a curve in a very kind of classical situation. It's not easy to say what the Betti table is. So you see, now we come finally to the result I wanted to talk about. There's some developments in the recent years. So the point was that no one even asked the question, what are the possible Betti tables? Because somehow it was thought to be very difficult, okay? For example, you see what can happen. It's not easy to find all Betti tables because, for example, what can happen is that when you have a Betti table, the Betti table doesn't exist, but its multiple does exist. It can happen, okay? So we have this example, for example, that goes like this. If you take the Betti table in 3 variables, this Betti table. So you assert that you want one generator, 2 linear relations, but among them 2 quadratic relations, and then 1 relation. This doesn't exist. Does not exist. And it's very easy to see because, you see, you have 2 linear relations. So this will be like 2 variables, x and y. But when you have 2 variables, x and y, you will always have the linear syzygy. So it forces this number to be non-zero. So this Betti table does not exist. But it's not difficult to prove that 2, 4, 0, 0, 4, 2 does exist. Okay, there are very concrete examples. So, you know, one knew about those examples, and it's not easy to decide when concrete Betti table exists. However, Boij and Soderberg, they were motivated by some conjectures so-called multiplicity conjectures about some inequalities between graded pieces of modules. And they came out with this really nice insight that they said, okay, let's not worry about which Betti tables exist, but let's worry about which Betti tables exist up to a constant multiple. Okay, so that was the insight. Okay, so what they did, they just say, okay, let's define the normalized Betti table. So basically, first of all, the first point is let's treat the Betti table as just a vector with rational coordinates. Okay, so beta of m we treat as a vector in the vector space over the rationals. Well, and there are infinitely many of those, so this will be 0n times z, right? Because columns go from 0 to n, and rows can go as far as we want. But now let's define the normalized Betti table. Normalized Betti table is just pi of m is just basically beta of m, but I normalize by, you see, where do I find the things that are not zero? When I have a non-zero module, obviously the sum number of generators has to be non-zero. So I divide by the number of generators, which will be beta 0i, beta 0j. Okay? And I consider just a set of those Betti tables. So basically, geometrically, what we might think of is that all Betti tables will lie in some kind of a cone. So this is a set of all beta of m. But then those pi of m normalized Betti table will kind of lie on some level. Okay? So when you have a cyclic module, like in all those examples, you just don't do anything. You have just 1, 0, 0, 0, then you just don't do anything. But if the module is not cyclic, you normalize. So they asked this question, what would be the set of normalized Betti tables? And of course, it's clear that what you would hope for is exactly what I drew here. The best possible situation I could dream about would be if it would be a nice polyhedral cone. Okay? And in fact, it turned out to be true. But Boij and Soderberg, they also had the idea about what would be the extremal rays in this cone. Okay? So the candidates for extremal rays are so-called pure resolutions. So what is a pure resolution? Well, a resolution is pure F1, F0 is pure basically if every generators of every of those modules are concentrated in just 1 degree. Okay? So let's just express it. So it means that for every I, there exists exactly one j, which I will call di, such that beta I di is non-zero, but beta ij is 0 for j different than di. Okay, so in our examples, basically most of the resolutions I wrote were pure. So of course the Koszul complex, remember the Betti diagram 1331, this was pure. 132 is also pure, but 111, 121, 11 is not pure. So how do you see the pure diagram? Well, basically this diagram is pure if in every column you have only one non-zero element. Okay? So that's, and of course now I have, for such pure resolution, I have the sequence of di's, so I would like you to notice that, so I call this d, the sequence of degrees, that I have to have, these degrees have to be increasing. because, remember, the map, the resolution has to be minimal. So the entries of matrices, now here they will have to be all of 1 degree because the resolution is pure, but they are of positive degree, so therefore the degrees are increasing. So these are degree shifts. And by the way, I didn't say it, so let me just say that in all of this, I'm now restricting myself to just this special case where actually m, dimension of m over k, is finite. Okay, so basically I only look at the modules which have only finitely many graded components. So this is, and in such case, by the way, one is guaranteed that this Hilbert process, the Sigid process, will continue all the way up to the nth degree. Okay, so what is known about those pure resolutions? Well, there was one thing that was known, and it was so-called Herzog-Kuhl inequalities, Herzog-Kuhl equations. So basically, what was known that, so suppose I have now this pure resolution. Suppose I have a pure resolution with degree shifts, d equals d0 smaller than d1, smaller than dn. So I have my exact sequence, and I know actually that this module is just finite dimensional. So mi is 0 for big I. And then basically again when I calculate this Euler characteristic and basically look at the coefficients of Hilbert polynomials, they have to be 0. So then the numbers beta I, which are those beta I di, have to satisfy equations, the system of equations, which is like this. So you see this will be the system of equations for this beta 0, beta n. And you see the first one is basically the Euler characteristic of our complex has to be 0. Then the second one is just I have to, again I have plus minuses, but now I multiply them by those degree shifts. Again, this has to be 0 because the next coefficient of the Hilbert polynomial vanishes, and so on. And I go to d0 n minus 1 minus d1 n minus 1 minus 1 to the n dn n minus 1. And then this has to be all zeros, but at the end I have to take basically dimension of n. So basically, again, this just comes from calculating this Euler characteristic. And it's sort of funny because, you know, at that point, it was not even known whether those things exist, okay? But, okay, they satisfy those equations. And what does it mean, you see? Well, here you see kind of van der Monde determinant, so it's a non-zero determinant. So up to a constant, there's a unique solution. Okay, so it follows, that there exists a R in, say, Q, such that beta I di equals, one can just write them dk minus d0 over, product is over k not equal to 0 and k not equal to I. Here's my R, divided dk minus di. So what this means from our point of view of normalized Betti diagrams, and that's extremely important, this means pi of such a pure resolution is uniquely defined. So without any knowledge of the pure resolutions, you know that what will be their normalized Betti diagram. Okay? So then, basically, Boij and Soderberg said, okay, so here's a conjecture. And the remarkable thing is that they conjectured with really almost no evidence. They just could prove n equals to 2, which is special for many reasons. But the conjecture is, well, okay, we are in an infinite dimensional situation, so let's first of all kind of reduce to the finite dimensional situation. So what we'll do, we have our Betti tables. We basically will fix a region such that we'll consider only the resolutions that have non-zero entries in this region. Okay, so what we do, we fix the lower degree shift and the upper degree shift. Okay, and now consider only resolutions. So consider now, let's see, B, the lower, the upper, will be just a set of all normalized Betti diagrams of graded modules, such that beta ij is 0 for maybe only for j between upper di and smaller di, lower di. Okay? So basically we look at all normalized Betti diagrams such that my Betti table is in this region. So this will be d lower and this will be d upper. Okay? But now you see, well, we can look at the pure resolutions that are in this region. Okay? So there are many degree sequences, degree shifts, which are in this region. Okay? So we can take another object. Oh, well, okay. Before I define that, let me point out one thing that I forgot to say, which is crucial, namely that the set of those Betti tables, of normalized Betti tables, is convex. This one can see right away. So the set of pi of m is convex. Because you see, that's actually extremely simple. Because suppose I have pi of m and pi of n, two normalized Betti tables. So these are some normalizations of beta of m and beta of n. But now look what happens. I can take direct sums of many copies of m and many copies of n. Okay? So beta of m direct sum p plus n direct sum q, well, you know, the minimal resolutions add up. So this will be p beta m plus q beta n. So when I normalize, by just taking the direct sums, I will cover all the points on the interval pi of m, pi of n with rational coefficients. Okay? So that's really the completely trivial observation. So this set is convex. So what can we do? Well, we know that in this region we'll have all those pure resolutions that are in this region. So we can take the convex Hall of all normalized Betti diagrams of those pure resolutions, such that this degree sequence is between d lower and d upper. By this, of course, I mean, you know, I order them coordinate-wise, right? I will say that d prime is smaller or equals than d double prime if and only if for every I 0n di prime is smaller or equals than di double prime. Okay, so this is a dream situation, and of course the point is that actually all of this turned out to be true. And at the beginning, kind of people did not believe this, but somehow not only they started believing it, but it was recently proved. So let me also point out, so this was kind of what was called the first conjecture, but it's actually even much more beautiful, because this convex Hall has a simplicial structure. And they also kind of conjectured about the simplicial structure. Because you see, if I fix this D, if I take the set of those pure resolutions, degree shifts, which are between D lower and D upper, this, of course, is a partially ordered set. Right? Well, I have this order. So there's a partially ordered set. And then to every partially ordered set, you can associate the simplicial complex. So if you have so let's call this sigma, maybe P, D lower and D upper. And then if I have partially ordered set, I can associate to it simplicial complex in such a way that you know, the simplices of dimension T are chains. X1, xt in P. So they actually conjectured that basically the structure of those resolutions, respect the simplicial structure. So so this is a conjecture, second conjecture. C, D lower, D upper has a simplicial structure of this, well, let's call this P goes to the simplicial complex sigma of P, sigma of this P, D lower, D upper. So for example, let's do some small example. In the situation where we are with the degree shifts, let's take the following 0, 1, 2. So here's the partial order set, 0, 1, 3, 0, 1, 4, 0, 2, 3, and 0, 2, 4. Okay? So this will be, from the point of view of free resolutions, this will be n is equal to 2. These are degree shifts. So I'm looking at all the resolutions which are, well, the lowest is 0, 1, 2 is here. Okay? Because I have 0, 1, 2. That's how the Betti table was defined. And the 0, 2, 4 is like this. So this would be kind of all possible pure resolutions occurring in this region. I would look at resolution in two variables. We're just having stars in this region. And then what is our simplicial complex? Well, in this case, it's not difficult to see because you see there are three chains of degree 3. It's three-dimensional. So there will be like two tetrahedra. Okay, so simplicial complex, let me maybe draw it here. This will be two tetrahedra joined at the one of the faces. Okay, so this will be 0, 1, 2, 0, 1, 4, 0, 2, 3, 0, 1, 3, 0, 2, 4. So you see what this would mean, that the simplicial structure, and that's what this conjecture number 2 would mean, is that you see, if I take a Betti table of any module, this normalized Betti table, well, the fact that in the convex hull, it means that it will be a non-negative rational combination of those Betti tables of the pure resolutions. However, the simplicial structure, the second conjecture tells you that our Betti table will have to be in one of the simplices. So it will be in a non-negative rational combination of only pure resolutions that occur in one maximal chain going from here to here. So you see, if it will be a resolution in this region, will be either a rational combination of those 4 or of those 4. okay? Or maybe if it's on the boundary, just of those three, okay? But so that's a very kind of strong statement. And actually, you know, what Boij and Soderberg were doing, they were actually doing numerical calculations, kind of assuming this, and it's always checked out. Whenever they took a Betti table of the resolution, and they knew about the pure Betti tables, they would see that indeed it was always the non-negative rational combination of the ones that were in one simplex. Okay?
Who raised this conjecture?
Excuse me?
Who raised this conjecture first time?
Boij and Soderberg, yeah. Yeah, it's all together, yeah. Boij and Soderberg, yeah, I should write it. So actually, the Soderberg was a student of Boij, and he actually already quit mathematics, okay? So there are two Swedish mathematicians. Okay, and then you see, it turned out basically that the theorem is true, okay? So that's maybe the punchline. All conjectures are true, and even more. All conjectures are true, plus more. So basically, you see there are two things that one needs to do. First of all, you have to fill the cone. You have to construct the pure resolutions, okay? Because even though Herzog and Kuhl knew what the Betti table is up to scalar, they didn't know whether they actually existed. So the first one was construction of pure resolutions. So this was done in the paper of Eisenbach, Floystat, and myself. And the remarkable thing about this is the following, that you see, well, in characteristic 0, this was construction characteristic 0, that if you just take A to be just treated as symmetric algebra of a vector space, E is our Cn, okay, then there's an action of the general linear group on this. Basically, this A will be just direct sum of the symmetric powers of Si of E. And each of this is irreducible representation of GLN. And the point is that one could construct those pure resolutions that are equivalent with respect to the action of this group. Okay? No one really understands why at that point, but it seems that there will be some hidden, some connection with representation theory. Because one would not expect it. Those extremal resolutions are supposed to be so special that somehow, why do we see always equivariant ones? But this maybe I'll explain more during the lecture later this week. And then Eisenbach and Schreier basically gave facet equations for the cone, and basically proving that there's nothing outside the cone. Okay, so this is Eisenbach and Schreier. And moreover, it's not that they only gave facet equations, but actually they those facet equations came from a quite unexpected source. Okay, namely facet equations, which somehow Boij and Soderberg did not see at all, and nobody saw. They come from vector bundles on Pn minus 1. So on the projective space, on the same vector space. It's complicated, so I will not explain. But the point is that they look at kind of the cone, well, the tables that look like this, at cohomology tables of vector bundles on Pn minus 1. So if you have a vector bundle on Pn minus 1, you have this infinite 0 up to n minus 1. So if you have vector bundle E, then the cohomology table, so E is a vector bundle. And basically in the row I, and for integer j, you put dimension of the cohomology group. And again, they form a cone, and they describe the extremal rays in the cone, and each extremal ray in that cone gives a facet equation for Boij Soderberg cone, and vice versa. Each excimal ray for Boij Soderberg cone gives a facet equation for that cone. See, it's not so simple as one might expect, that maybe the duality is like that. Okay, because you see here I have from 0 to n, so this one is wider than that one. But okay, but they construct all those functionals, and again, the extremal rays here have a representation theoretic meaning. They are so-called supernatural vector bundles, but again, one can construct the equivariant ones, okay? And somehow, so this gives this beautiful duality that really no one yet understands exactly what it comes from, but it solves this basic problem of classifying the Betti tables up to rational number, okay, up to a multiple. So I think I'm out of time.